I'm going to produce 4 colors of shirts. Demand for these colors we assume are independent. We will later can discuss what will happen if they are dependent and if there is a correlation between their demands. Well, for the time being, we assume that the demands are independent. And the demand for all of them over a specific period is normally distributed with average of 100 and a standard deviation of 25. If we die them first and want to have a 97.73 service level, we want to know how much safety stock do we need. And I have chosen 97.73% service level because it is 2 standard deviation to the right. Therefore, Z of that service level is equal to 2. And we have the standard deviation, and we can simply compute the safety stock for each product, which is 2 times 25, and that is 50. And because we have 4 products, then the safety stock for all 4 products would be 200. Now, suppose we postpone differentiation. We do not dye these fabrics and leave it as a blank fabric and wait for the demand, because demand of red may go up, demand of green may come down. But if we do not differentiate, when one goes up and the other comes down, they compensate for each other's, and we don't need too much safety stock. So now we assume that we have a fast machine. It can paint this shirt 2 different colors as demand come in. Now this new shirt is aggregation of 4 other shirts. And that general rule of statistics is over there, that when we add several random variables together, their averages are added, but their standard deviations are not added. Their variances are added. And because here we assume that average and standard deviation for all products are the same, therefore average would be 4 times 100, but standard deviation will not be 4 times 25. It would be variance, which will be multiplied by 4. Therefore, variance for each of these products would be 25 squared, and then we have 4 of them. And that is variance of summation of these. And then if I'm going to go from variance to standard deviation, all I need is to put a square root over there and a square root here. And for that, square root of 25 to the power of 2 is 25, and the square root of 4 is here. Therefore, standard deviation would be square root of the number of variables times the standard deviation of each one. If I go this way, the standard deviation of the undyed fabric would be 50, and when I multiply it by Z of the service level, standard deviation would become 100. So I was able to reduce 200 to 100. I was able to reduce 200 to 100. That is 50%. That is one benefit of postponement, delayed differentiation. Look at Home Depot, Lowe's. Suppose they have 100 different colors, paint colors. Indeed, they have thousands of different paint colors. Suppose demand is 30 per week and the standard deviation of demand is 10. And suppose you want to keep a service level of 95%. Instead of 95% is 1.65, multiplied by 10, that would lead to a safety stock of 16.5 for each product, and we have 100 of them. Therefore, we need 1,650 pounds of product, for example, pounds of paint over there. But now, they have postponed the differentiation. These colors are there, and then they combine different colors with that, and they can make infinite colors. But now we would like to stay with this 100. We added 100 products. A standard deviation is the square root of 100 multiplied by a standard deviation of each, and therefore standard deviation is 100. And if we multiply by Z of 95%, which is 1.65, that means we need a safety stock of 165 to have a service level of 95%. That is 1,650 compared to 165. Let's go through another example. Suppose Epson produces printers for sale in Europe and the factory is in Taiwan and lead time is 6 weeks. Average demand, standard deviation of demand per week, lead time is 6 weeks, 96%. Each of these countries need their own power outlet and their own user's manual in their own language. Now suppose these are all produced in Taiwan, differentiated in Taiwan, and are sent to Europe. Let's see how much safety stock do we need. Let's look at France, for example. Average demand per week is 30,000. Lead time is 6. Therefore, lead time demand is 6 times 180. Standard deviation of lead time demand is the square root of lead time times the standard deviation of weekly demand. And that would come out with 18,000. Z of 96% is this one. If we multiply it, we need 32,182 as safety stock. Here I have average demand for each European country, standard deviation of demand, if 6 weeks lead time. Therefore, this is average during lead time. This is standard deviation of demand during lead time, Z of 96%, and this is safety stock. I can do it for all countries and then add it up. In the decentralized system, I need this much safety stock to have a 96% service level. Now suppose Epson has decided to create a central DC in Europe. Do not differentiate the printers, make them modular such that you can easily plug in the power supply and put the manual over there inside the package. So we have a centralized system. Therefore, we can add these numbers together and multiply by 6 and get this number, which is average demand during lead time. It is multiplied by 6. But when it goes to standard deviation, it is not standard deviation which is multiplied, but it is variance. Here is a standard deviation of 6 weeks demand. We square it and get this number, which is variance, variance, variance. Then we add all variances together, and then we put it under the square root to get standard deviation. And then we multiply it by Z of 96%, and we get this, 65,000 compared to 150,000. This one is 43% of this one. Such an improvement. Thank you for your attention. This is the advantage of postponement. It is the same as the advantage of centralization. We saw it also in EOQ. We have seen this centralization in waiting line analysis too, when we have two servers performing independent of each other. The performance metrics are much compared to when we combine them. Thank you very much for paying attention to this discussion on postponement.